Okay, we're gonna do determinants. Um, so first, we're gonna start with a definition of determinant. However, our definition will require the definition of what a permutation is. So let's talk about permutations first. Permutations. Um, when we have a set of objects, um, every time we rearrange the objects, then we have a permutation. So let's say we have those objects. There we go. And so if they're in that order and we rearrange them, so that's a permutation. That is a rearrangement of the original setup. So that was the original setup. If I do this, that's another permutation. So if you have three objects, there are six permutations because those two can swap. That's one permutation from the original. Or those two could swap. That's two. Or those two can swap. That's three. Um, or we can move that this way, four, or we can move everything, oh yeah, this way to the left, and then that's five, and I'm missing one, but I already lost track of which ones. That's why it is easier to just use letters or numbers, and instead of just um, um, objects. So let's start with A, B, and C. A, B, and C. How many permutations are there? I already said there are six, but let's look at them. So CB, ACB is one of them, or we can have BAC or BCA. Okay, so that's the one of those I was missing, I believe, when I was doing the objects, or CAB or CBA. Yeah. So the way I come up with a systematic way, or I find all the permutations in a very, very systematic way. So if, let's say we have, I'm going to show you how I do this. If you have four objects, um, A, B, C, D, the first thing I do is I just swap those two and keep that. So A, B, D, um, A, B, D, C. There we go. All right. So AB is already done. What I mean by that, AB on the first two spots is already done. Then I keep the A and I go with C, and then there is BD left over, BD. And then I swap those two again, AC, um, BD. And then I move on to A, AB, AC, AD. So there's going to be two with AD, whoops, AD. And then there's going to be two. No, that's it. You can only have, if you have A on the first position, you can only have B on the second position, or C or D. So that covers, so this finishes up all the A um, at the beginning, permutations. And then in the same manner, there's going to be six of them with B on the first position, six of them with C on the first position, and six of them with D on the first position, making a total of 24. So there's more here. There's more that I'm not going to write down, but there's a total of 24 permutations. Now we count the original one as one of them. So here there are six permutations. So there are 6, 24. If we have only two elements, A, B, there are only two permutations. So A, B, B, A, so there are two. So we go from two elements, two permutations, three elements, six permutations, four elements, 24 permutations. If we had five elements, we would have 120 permutations. And the reason is this. Um, if we had D here, D, D, then what would we have on the other three? We would have A, B, C. And then we would have to move those around. And we know there are 6 ways to move those around. Okay, so there is 6 of that. 6 of those A, B, C. You know, you put the A, B, C, and then A, C, B, and then B, A, C, B, C, A, C, A, B, C, B, A. All right, so those are the 6 ways of rearranging this. Those 3 when we have D. Well, when we have A, we have after A 3 elements, and there are 6 ways to rearrange them. So okay, and if we have 2 elements, there are 2 ways to rearrange them. If we have A on the first position, or C, even C is better because we already have the A, B, and B, C here. So if we put C on the first position, there's 2 ways to do this, A, B, or B, A. And then if we have B on the first position, there's 2 ways to rearrange the last 2. Okay, so one kind of builds onto the other. This 2 shows up in here. Those 6, all of the 6, show up here when D is there. So they build up one on top of the other. So let me make a quick table here. Number of elements to be permuted and number of permutations. Okay, so if we got 2 elements, there is 2. That's easy. If there are 3 elements, well, the first element in the rearrangement can be one of those 3. And then we have 2 ways to rearrange the last 2. So that is 3 times 2. 3 times 2, which is 6, equals 6. If we have 4 elements, as in this case, the first letter or the first object to be permuted can be any of those 4. And then the last 3 can be rearranged in the same way as those 6 could be rearranged. So there are 6. 4 times 6, which is 24. Or another way to write that down is 4 times 3 times 2. Okay. And then if we have 5, well, the first element could be any of the 5. The last 4 elements can be rearranged in any of those 24. Yeah, 24. So that means 5 times 4 times 3 times 2. That number is called 5 factorial, or abbreviated as 5 factorial. 5 times 4 times 3 times 2 is 5 factorial. 5 times 3 times 2 is 4 factorial. That's 3 factorial. So this, we use the exclamation symbol for the factorial. And that is also 2 factorial. Yeah. We also have 1 factorial, which is 1, and 0 factorial, which is also 1. However, the matrices that we're going to be working on are at least 1 by 1 or 2 by 2, really. So we're not going to worry about 0 factorial or 1 factorial, really. So just to emphasize, 2 factorial equals 2. 3 factorial equals 3 times 2, which in turn is 6. 4 factorial is 4 times 3 times 2. Now, we already know 3 times 2 is 6, so we'll multiply by 4, and that gives us 24. 5 factorial is 5 times 4 times 3 times 2. I was going to put times 1 because that does not change, and that kind of makes the list more complete. So you can multiply by 1 on all of them. So then we have a nice list, 1, 2, 3, 4, 5. Anyway, that's going to be, okay, so we already know 4 through 1 is 24. Multiply the 24 with a 5. That's a factorial. That gives us 120. And then 6 factorial is going to be, what is it? 6 times 5 times 4 times 3 times 2 times 1. So that is, so 5 through 1, we already know is 120 from the previous line. Multiply that by 6, that gives us 720, and so forth. I think the next one is going to be 5,040, if I'm not mistaken, and so forth. Also, 1 factorial is 1, and 0 factorial is 1. So 1 is the two of those. Many of us think this is confusing, and it sort of is confusing, but if you think of having no multiples of anything, that is the same thing as multiplying by 1. So that's why the 1 is there. Anyway, so that is the factorial, and that gives us the number of permutations we have. Okay. Let's look at permutations of numbers. Well, now let's stay with A, B, and C. Okay, let's go back to 3 objects. 3 objects. It doesn't matter what the objects are. They can be, an office, like items such as a clip, a pencil, or they could be letters A, B, C, or they can be numbers. It doesn't matter what we are permuting. Anyway, so we have A, B, C. We're going to attach to any permutation a parity. So ABC is the original arrangement of those 3. And by the way, that is arbitrary. So I'm saying this is the original arrangement. Somebody else could say, well, what about CBA? Sure, that could be your original. It doesn't matter. So, but it is, I guess it does matter. It is arbitrary. So I'm calling this the original one. How many swappings do I need to put it back into the original one? That's kind of an odd question to ask. It's one of those odd questions that we have in math. Is a line parallel to itself? Yes, it is, which is kind of weird because we never, ever, in regular speech, we compare an object with itself. We don't say, oh, this pencil is parallel to itself, or this pencil looks like itself. That's kind of weird. But in mathematics, we allow that to happen. So how many swappings of letters do we need to come back to this arrangement? Well, that's 0. So the parity is even because there is 0 rearranged, 0 swappings. This parity is going to become more clear as we do more examples. Now, how about A, C, B? How many swappings of letters do I need to do to come back to the original one? Well, if you swap B and C, we get back to that. So that requires 1 swapping. So this permutation is odd because it requires 1 swapping. So the number of swappings gives us the parity. Okay, how about B, A, C? Now let's pretend I want to move this back to that. Okay, here we need to swap those 2 to put us back into this. If we swap those 2, nope, we don't get back. If we swap those 2, nope. If we swap those 2, oh yeah. If we swap those 2, then we get back to ABC. That's 1 swapping. So the parity of this permutation is odd as well. Okay, how about BCA? How many swappings do we need? Okay, we can swap the first 2. Nope, that doesn't do it. The last 2, nope, that doesn't get us ABC. If we swap A and B, we get ACB. We get this guy, but we don't get ABC. So we cannot do this with 1 swapping of letters. We have to do this with 2 swappings of letters. So swap A and B, I'm going to show you. So 1 swap of A and B, and there's many ways to do this, will give us ACB. Now swap CB, and that gives us ABC, which is the original one. This is the original one. We declared that at the beginning. Okay, so we need 1, 2. 2 means even. Yeah. How about B? No, we finished the B's. So now we're going to do C. I don't want to erase, so I'm going to put C. Let's erase, because otherwise we're going to get out of alignment here. Okay, so C AB. How many swappings do we need to get back to ABC? Let's see. Nope, nope, nope. So we need 2 at least. So swap those 2, and that gives us ACB. Swap CB, and that gives us ABC. So that means we need 2. Consequently, this permutation is even. Even. 1, 2, 3, 4, 5. There are 6 of them, so I'm missing 1, CBA. That requires only 1 swapping. All we have to do is exchange. Well, I don't need an arrow, I guess. I can just show. If you swap A and C, we got ABC. So that is 1 permutation, and that is an odd permutation. So all the permutations are always split up into half of them are even and half of them are odd. Even, I'm going to put an E for even, odd, odd, even, even, and then odd, odd, odd. So we have 3 even and 3 odd permutations. Excellent. And we can rearrange always permutations into even and odd. Yeah. So I'm not going to do all of the 4 permutations of 4 elements. I'm going to switch to numbers now. So let's call this example. Let's just label this as example 1. Okay. And let's say we have 4 elements, 1, 2, 3, 4. Those are the elements, numbers themselves. And there are 24 permutations. This one is even. We're going to label this as the original one. By the way, if we're doing permutations of numbers such as 1, 2, 3, 4, the regular normal order they come in 1, 2, 3, 4. That's our original. We're going to label that as our original permutation. Because we want to know how many swappings takes to go back to that original one. So here, since this is already original, it requires 0 swappings. 0 is an even number. And so this permutation is labeled as even. An odd permutation is the one that requires 1 swapping, or 3 swappings, or 5 swappings. So 1, 2, 4, 3 will be odd permutation. How about 1, 3, 2, 4? Let's see. Oh, that's odd. How about 1, 3, 4, 2? So swap those 2. Swap those 2. So the 2 is here, and the 4 is in its place. And then swap the 3 and the 2. Yep, so that is going to be an even permutation. And there's going to be, I'm not going to put all 24 of them. But then once we have all 24, we can classify them into even. We can put all the 12 of them on one side of the page, and then all the other 12 on the other side of the page. So we're going to have the even ones on one side, the odd ones on the other side. So we need to understand what a permutation is. Excuse me. And then we can have 5 elements, in which case we will have 120 elements. 60 of them are going to be even, 60 of them are going to be odd, and so forth. And we just go by the number of swappings. Yep. And that will tell us. Okay. So determinants. Yeah. So now let's define what a determinant is. And we're going to go by defining the determinant of a 2 by 2 matrix, and then a 3 by 3 matrix, and then a 4 by 4 matrix, and so forth. So 2 by 2 determinants. Okay, so let's say you have A11, A12, A1, rather 21, A22. There are different symbols for determinants. We can call, so first the notation. If you have two bars, very much the same as the absolute value bars. If you have two bars around the matrix, that is, or even just the elements of the matrix, that means the determinant. So that is not a matrix, it is the determinant of the matrix, which we're about to define. The determinant of a matrix is going to be a number. Now, if this matrix, the matrix with those entries, is labeled A, capital A, then we can also write this as DET for determinant of A. Okay, so this is just notation. I'm not telling you how to come up with the actual number. This is just the notation. Okay. Now, we have 1 and 2. Those are the numbers involved in this setup. And we are always going to label the entries this way. The first number is going to be the row, and the second number is going to be the column. So this means first row, first column, first row, second column, second row, first column, second row, second column. By the way, technically speaking, there should be a comma in between 1 and 2, because otherwise this reads as 11, 12, 21, and 22. But that's not really what we mean. We mean 1, 1, 1, 2, 2, 1, 2, 2. Technically speaking, again, there should be a comma in between. When I'm writing this, if the context is clear enough, I don't put the commas because it is clear that we do mean 1, 1, 1, 2. But technically speaking, there should be a comma in between. Okay. So the question is, what is the determinant? Okay, we're going to form products in which we will have the first coefficient, the first sub-index in order, A1, A2, that's it. And then the second sub-indexes are going to be permutations of 1 and 2. So 1, 1, 1, 2, 1, 2, 2, 1. Okay, this is a little confusing. It will be easier if we had a bigger matrix. Perhaps we should do that with a bigger matrix. Let me finish this up though. So this guy is the permutation 1, 2, this product, we're multiplying those two numbers, that product refers to the permutation 1, 2. This product 2, 1, this product refers to the multiplication, rather to the permutation 2, 1. Yeah, that's a permutation. If we had more numbers, as we will do in the next idea, topic, subtopic, it will make more sense. Okay, this permutation is even. This permutation is odd. And consequently, we're going to label this as positive, this product, and this as negative. And the sum of that product with this product will be the determinant. I'm going to do a 3 by 3 because that, when an example is too easy, then when an example is too easy, then it almost loses its idea. Okay, let's say we have 3 by 3. A11, A12, A13, A21, A22, A23, A31, A32, A33. There we go. Okay, so we got 3 by 3. Yes. How many permutations of 3 elements are there? Well, there are 6. Okay, so we're going to put down A1, A2, A3 6 times. 1, 2, 3. 1, 2, 3. By the way, we're missing the second index. Notice that the indexes there are 2 indexes. in every element. So here, this is not finished. I have to place a second index on each one of those A's. But I want to show you how this is formed. A1, A2, A3, 1, 2, 3, 4, 5, one more, 1, 2, 3. Okay, so we got the first index is fixed of the A's. And these are going to be products. We're going to multiply this A with this A with this A. Then we're going to multiply this with that with that. Then we're going to multiply this, and so forth. Okay, for the second indexes, we're going to have permutations of 1 to 3. So 1, 2, 3 is this product. So multiplying this guy with this guy with this guy corresponds to the permutation 1, 2, 3. Then we're going to change the permutation. There are 6 of them. 1, 3, 2, 1, 3, 2. So this guy, and this guy are going to be multiplied together. So first we started 1, 2, 3, then 1, 3, 2. Then we finish up the ones that start up with 1. Now we're going to have one that starts with 2 as far as the permutation, such as 2, 1, 3. 2, 1, 3. Perhaps that is easier if we go from the permutations to that. 2, 3, 1. 2, 3, 1. 3, 1, 2. 3, 1, 2. 3, 2, 1. 3, 2, 1. Okay. So now we have those products. Let me just show you. So so the first one, 1, 2, 3 goes 1, 2, 3. 1, 3, 2, 1, 3, 2. 2, 1, 3, 2, 1, 3. But then we have 2, 3, 1. And then 3, 1, 2, and 3, 2, 1. And those are all the possible ways to multiply one element from a row with an element of one column by elements of different rows and different columns. Anyway, the parity of this guy is even. If we have an even parity, we assign plus to this product. The parity of this guy is odd, so minus. This guy is odd because all we have to do is switch the 2 and the 1, minus. Here we need 2, yeah, because the 2 and the 3, no, we swap those 2 and then we swap, so we need 2 even. This one requires, let's see, 1. If we move the 1 over here and the 3 over there, yep, it requires 2 even. This is odd because all we have to do is swap the 3 and the 1. There we go. If we add those 6 numbers, we're going to end up with the value of the determinant of the matrix A. We're going to assume that this matrix is going to be A. Okay, let's do an example. Example 2. An actual example 2. Okay, so let's find a determinant, say 3, 4, 5, 6, 7, 8. How about 2, 1, 9? Okay. So this is a 3 by 3 matrix for which we're finding its determinant. Let's label this matrix as matrix A. Matrix A. Yeah. And then we're finding the determinant of that. Okay. So we have the products. If we pick one element from each row and one element from each column, we have 3, 7, 9. Boy, that's a big number. 3 times 7 times 9. or we could do 3, 8, 1. 3 times 8 times 1. See, first row and first column. So I cannot use that. Once we pick an element, we cannot use that row or that column. So let's go back to 379. If I start with a 3, cannot use that row in this column. Those two are gone. So I have to pick a number from this guy, this square. So 7. Okay, but then we cannot pick an element from that row or that column, nor from that row or that column. So the only number left is the 9. If we start again with the 3, as in this case, wipe off that row and that column. If we pick the 8 instead, that's fine. We pick the 8, but then we cannot pick an element from that row or the column of the 8. So that gives us the 1. That's why we have to have 1. So we're wiping off rows and columns. If we start with 4, that's fine. Then I cannot use that row or that column of the 4 anymore. 6. I cannot use that row or that column. So the only thing left is the 9. 4, 6, 9. And we're multiplying those numbers together. Or we could do 4, 8, 2 times 8 times 2. Or we can do 5, 6, 1. Or 5, 1, 2. No, rather 5, 7, 2. Okay. So let's multiply those. That's easy, 30. So I'm going to start with the easy one. That's 70. Notice that I'm leaving some space here because we have to assign a assign to them. 4, 8, 2. That's 64. 24 times 9. That's too hard. 6 times 9 is 54. 108. 216. 381. That's 24. 63 times 3. 63 times 3, so that's, I believe it is 189. Okay, but then we're gonna assign signs to them. So this guy is that corresponds to the permutation 1, 2, 3, which is an even permutation. We're gonna keep this as positive. 3, 8, 1 is an odd permutation because that corresponds to 1, 3, 2. So so I'm going to put the permutations here corresponding to how we're picking the elements. 1, 3, 2. So the first one was 1, 2, 3, which is even. 1, 3, 2 is odd. We're going to have a negative. Because how do I know it's odd? Because it requires the swapping, one swapping. And then we end up with the original 1, 2, 3. 4, 6, 9 comes from 4, 6, 9. So that is 2, 1, 3. Column 2, column 1, column 3. 2, 1, 3. That's odd because all we have to do is this, negative. This guy, 4, 8, 2, 4, 8, 2 comes from column 2, column 3, column 1. 2, 3, 1. Swap those two, and then we have to swap. So that's an even plus. That goes with that. That goes with that. There we go. And by the way, we gotta preserve the negative here. Negative, negative, plus this guy. Well, let's see. 5, 6, 1. So that is 3, 1, 2. 3, 1, 2. And swap those two. That's even. And then we're gonna have 3, 2, 1. 3, 2, 1. which is odd because all we have to do is swap those two there. So this is negative and positive. Then we add all of those numbers. Let's say 9 and 4. 9 plus 4, 13. I'm sorry, we're subtracting. 9 minus 4 is 5. Oh, that's not going to work. Let's put together the positive numbers. 9 and 6 is 13, and 0, 13. Carry 1. 9 with a 1, and 6 is 15, 18. Carry 1, and 1 is 2. But then we got to add the negative numbers. 4 and 6 is 10. We carry 1. And 2 is 3, 4. And 7, 11. Carry 1. 3. Okay, so it looks like we are going to subtract. So 0, 10 minus 3 is 7. This is going to be a negative number. 10 minus 8, 2. So it looks like we end up with negative 27. I'm going to pause for a moment to check that I'm correct using the graphing calculator. Yep, I checked with the calculator, a graphing calculator. What I did is I edited the matrix. There it is. It has the same elements, 3, 4, 5, and so forth. And then you go out. I'm sure you can find many places. You don't necessarily have to have a graphing calculator now with the computers or phones or the internet. And then I found the determinant, and the determinant, you can find it under matrices. Let's see, matrices. And then there is the math, and the first choice is the determinant. And then once you have the determinant, you can put the name of the matrix, and let's exit. And then you press enter, and the calculator will do this. So the 27 comes from all of these computations. Now there are ways to do this, you know, they teach in other places. Like you can add this row to here and add it to that, and then you do up and down multiplications. No, I think they go up and then down diagonally the other way, and one is positive, the other one is negative. I forget which one is which. But it boils down to just a shortcut for this. The only problem with that multiplication for determinants is that I don't know if it works for 4 by 4. It works for 3 by 3, but I don't know if it works. I don't know. I don't apply that. What I do is just this pretty much every time. By the way, in quizzes and tests and assessments, I'm going to ask you to please use nothing more advanced than a basic calculator. Something like this will be because I'm not going to necessarily ask you to do big multiplications by hand, you know, like 189. So those we can easily do with those calculators, and then the additions you can do with the calculator too. But a simple calculator like this, you can double check your answer, but don't show, I mean, just to check to make sure that you didn't make any mistakes on the computations, but don't just give an answer without the work, because we need to show the work. So that is a determinant. If we have a 4 by 4 determinant, then we will have a long list. This list was 6 items that we added or subtracted, you know, 1 for each. But if we had a 4 by 4, we would have 24 of them that we need to add or subtract. And it is a good idea to go through that at least once, just to understand what's going on, especially when we deal with the parity. Okay. The other complication we could have, example 3. So I'm going to copy the same matrix, 3, 4, 5, 6, and you're going to see why. Actually, initially it's going to be the same, but I'm going to make a change. 2, 1. So example 2 was this matrix. The only thing I'm going to change is the 9. The 9 is going to be negative. Okay. That's the ink running out of the pen. I don't mind too much because I'd rather have it oh, it's the other way, I think. Anyway, oh, the negative 9. How are we going to address the negative 9? Now, the numbers we got here are 189, negative 24, negative 216, 64, 30, negative 70 from those products. The ones that have the 9 are going to be altered because instead of a 9, we're going to have a negative 9. So even though this is plus, because this number is going to be a negative 9 multiplied with 21, instead of having plus 189, we're going to have plus negative 189. So this guy is going to be negative. If we put a negative here, no 9, so that doesn't change. This one has a 9, so this one would be replaced with negative. Yeah, so that gets a little complicated because in addition to these signs are going to be fixed. You're going to keep those. But in addition to that, we're going to have if any of those numbers has a negative in it, we have to include that into the product. So this would be negative 9 instead, and then we would have two negatives, the negative from the parity of the permutation plus the negative from the 9. So this 216 would have to be positive. Positive. Then going down the list, no 9, no 9. So the 9 only shows up twice, which means that in this determinant, we will change 2, that guy and that guy. And that's going to change the value of the determinant. Is it going to be positive 27? Well, let's find out. The positive numbers are going to be 1, 2, 3. And by the way, we don't necessarily have to preserve 3 negatives and 3 positives. I don't think that's the case because you could have more than one negative number. Anyway, that's going to be 60, 70, 80, 280, 310, 310 positive. And then the negatives, let's see, 9, 13, carry 1, 9, 11, and 7, 18, carry 1, 2. So we have 0, minus 3, 7, 10 minus, no way, positive 27. If we change 1, I don't know if that makes, I don't know if that was coincidental at first sight or not. Was that a coincidence? Let me quickly change here, and this is actually not bad for students to see. Let's go to matrices. Let's edit this matrix. Yeah, so this number, we're going to change it to negative 9. Then I'm going to go out here, and I'm going to repeat this. And yeah, we get 27. So yeah, that computation is correct. I think that was coincidental, though. I'm not sure that changing one sign will change the whole thing. Let's do a quick one. Example 4. All right, so a matrix that let's do an easy one, such as 1, 2, 1, 3. So the products are going to be way faster here. So 1 times 3 is 3, and then 1 times 2 is 2, but that's a 2, 1 permutation that comes from column 1, column 2, which is a permutation. So that's going to be a -2. And by the way, this is really 1 times 3. I'm going to rewrite it. So 1 times 3 minus 1 times 2. So we have products. And that turns out to be 3 minus 2, which is 1. Now let's change that to a negative. So this is example A, example B. 1, 2, 1, -3. So we will have 1 times -3 minus, because of the permutation, the additive of 1, 2, 1 times 2. So 1 times -3 is -3, minus 2 is -5. Yeah, so we get 1, and changing this gives us -5. I believe that is completely coincidental, that we end up with just the opposite. That is totally, totally freaky coincidence. Because if we change only one element, the sign of one of the elements, if the rule was the same, then we would have the opposite. And in this case, we don't. Anyway, we're going to come back to this example 2 in a moment. There are some properties that are important to properties of determinants, and they can help us evaluate determinants. Yeah. So the first property is that determinant of the identity matrix, it doesn't matter what size it is, will be always equal to 1. Because most of the products are going to be 0. Let's say you have a 3 by 3 matrix. So I'm not going to prove it, but I just want to show why it makes sense that it is going to be 1. If you multiply, 1 times 1, you get 1. But if you multiply 1 and not this, you don't choose this column and this row, you have to choose an element that is outside of this in the same row. So the only other elements are zeros. So 1 times 0 times 0 is going to give you 0, when you do products of the multiplications of the elements. If you multiply, and then if you start with 0, then you end up with 0 and 0. So there's a lot of zeros. So a lot of the products are going to be 0 anyway. Here there's 6 products. 5 of them are going to be 0. The only way we cannot get 0 is if we precisely pick 1, 1, 1. And the same thing will happen if you have a 2 by 2 matrix, or a 4 by 4 matrix, or a 5 by 5 matrix. There's going to be only one product that is not going to give us 0. All the other ones are going to give us 0. So when we add them all together, you end up with a 1 plus a bunch of zeros, or minus a bunch of zeros. We still end up with a 1. So once we have that definition of determinant, that is straightforward. If we just look at the matrix. There is another property I'm going to add. This is property number 1. That's not kind of looks like a D. I'm going to label it as property number 0. The determinant of any matrix A. So by A, we mean any matrix, any square matrix, is going to be a real number, is a real number. And we're assuming that the entries on a matrix are going to be real numbers. So we're not going to have infinity or negative infinity, or it will not happen that the determinant does not exist if the matrix is a square matrix and the entries are real numbers. So determinants always will exist. And if we have matrices, real matrices, then the determinant will be a real number, a single number, such as 27, such as negative 27. Okay. Property number 2. I know this is kind of weird because I did 1 and then I went back to 0 and then 2. But now I'm going to try to go in order. If you swap 2 rows of a matrix, then the determinant is going to be opposite. The corresponding determinants are going to be opposite. So assume A and B are same matrix, except that um, 2 rows have been swapped. Yeah. So if 2 rows have been swapped, the determinant of one, it doesn't matter which one, is going to be the determinant of the other. Oh, no, they're not going to be equal. They're going to be the opposite. One is the opposite of the other. It doesn't matter which one is you put the negative on. They're not equal. One is the opposite of the other. So, yeah. Let's do an example. Now, we're going to piggyback on example 2. Okay. So, example 5. Example 5. Now, again, I'm going to use example 2. So, example 2 is this guy, 3, 4, 5, 6, 7, 8, 2, 1, 9. If we put down 3, 4, 5, and then the last row next, 2, 1, 9, 6, 7, 8, and you already know what the answer to this is, and we have exactly the same matrix, except that the rows have been swapped, the second row and the third row have been swapped, then I don't have to do all of these computations again. I can simply say, oh, well, the answer is, if this was negative 27, positive 27. And then if we switch those two, the determinant of that matrix after switching those two will be negative 27. So swapping rows will give us simply the opposite number of the determinant before swapping rows. And if you swap rows twice, well, then you end up back to the same original determinant. So we can make a note of that. That is from example 2. Yeah, after swapping the rows. So that's what we mean by this rule or this property. If you swap 2 rows, you don't have to redo the matrix, the determinant rather. All you have to do is change the sign of the determinant. The determinant is the number, by the way. Now, once we know the parity of the permutations, it does make sense because swapping rows is equivalent to doing an extra change, an extra swapping. So whatever was odd, by adding one more, you end up with even, and whatever was even, by adding one more swapping, we end up with an odd. The parity changes exactly in the opposite way, and that's why we end up with exactly the opposite answer. Okay, that can be handy because if we are already familiar with a certain matrix and the other matrix has the same kind of rows but swapped, no problem. Okay. Properties, yes, back to the properties. Oh, the determinant is row linear 3. Determinant is row linear. By that, what we mean is that if we multiply a row by a scalar, okay, so, yeah, so let me continue over here. So continue properties. Yeah. So start with matrix A, okay? If we multiply one row, it doesn't matter which one row by K, then the determinant multiplies by K as well. Now, one row, but any row, it's got to be one row. Okay. Example 5. Example 6. I'm going to use example 5 now that we have that handy. So let's say I multiply the first row by 2, just the first row. You can multiply any row. So 6, 8, 10, 6, 8, 10, 2, 1, 9, 6, 7, 8. What is the determinant? Now, technically speaking, if I wanted to do this from scratch, we will have to have all the products, 6 times 1 times 8, minus 6 times 9 times 6, plus 8 times, no, it would be minus 8 times 2 times 8, plus 8 times 9 times 6. And I forgot whether it was plus or minus for the next one. 10 times 2 times 8, and then 10 times 1 times 6. Anyway, so we will have to do all of those products, figure out the parity, add positives, add negatives, put them all together. So it's a lot of work. But if we notice that this is exactly twice as much as that for one row, then all we have to do is double up the 27. The answer is 54 there without doing any product. So knowing those properties is very, very handy. Can be extremely handy. Yeah. Now, example 7, if we multiply the second row by 2 again, we would have 6, 8, 10, 4, 2, 18, 6, 7, 8. So because from here to here we multiply one row by 2, the determinant will be double that, 108. But if we multiply, well, comparing this matrix with this matrix, if we multiply the first and the second rows by 2, then the output has to be multiplied by 2 times 2. Because every time we multiply a row by a number, we got to multiply the output by that number. Yeah, so watch out, because, okay, that can be a little confusing. Okay, so for determinant purposes, determinants, we multiply one row. Multiply one row. It doesn't matter which one. Multiplying one row multiplies the determinant. But for matrices, we cannot just multiply one row when we're multiplying something. Let me give you a quick example. Let's say you have 3 times 1, 2, 4, 5. This is a matrix. That's why I'm using those, not a determinant. When we multiply with 3, we got to multiply every element by 3. So this is equal to 3, 6, 12, 15 as a matrix. Okay, so watch out because I'm just looking at the determinants. I mean, rather at the properties. From property number, the last property we wrote down, which was property 3, and we haven't finished property 3. Property 3 is a big property, by the way. It's a biggie. So we're going to spend a little bit of time on it. But from property 3, we can say that if you have a determinant of a matrix A, which is multiplied with a constant K, okay, that means that every row gets multiplied by that constant. And if the matrix is n by n, then we're multiplying the first row by k, the second row by k, the third row by k. So we have n k's. So we will have k to the n times the determinant of A. Yeah. Yeah. Let me give you an example, a quick example. Let's go back to our example 2. Okay. So let's say we want to find, let me make an example out of this, example 8. Let's say we want to find the determinant of, let's do 5. 5 times the matrix in example 2. 3, 4, 5, 3, 4, 5, 6, 7, 8, 6, 7, 8, 2, 1, 9. Okay, the determinant of 5A, pretend that is A. Determinant of 5 times A. Now, we know the determinant of A is 27. So if we were naive, we would say, well, that is 27 times 5. But that is not correct. We're going to fix this. That is not true because when we multiply by 5, we're multiplying every element in the matrix. So we would have 15, 20, 25, 30, 35, 40, 10, 5, 45, which means that the first row gets multiplied by 5, the second row gets multiplied by 5, the third row gets multiplied by 5, and that means that we are actually multiplying the determinant by 5 3 times. That's what I mean by k to the n, k to the 3 in this case. Okay, now it is good, because every time we multiply one row, we got to multiply by 5. That is 125 times 27. And I'm going to use this calculator. 125 times 27. And that gives us 3,375. So the determinant of 5 times that matrix is going to be that huge number, 3,375. Now we are saving ourselves a lot of time because instead of multiplying through, 15, 20, 25, 30, 35, 40, 10, 5, 45, and then doing those products, snaking around, and then figuring out the oddity and all that, we can simply just use this formula. Yeah. And likewise, you can factor things out, and then when you finish with the determinant of something that is hopefully simpler, then you can just multiply back by that number. Just make sure you include as many of that numbers as the size of the matrix. Okay. So that is just the multiplication. That is one part of the linearity, the row linearity. So we're still working on the row linearity, still talking about row linearity property. I didn't explain why, but I hope it is clear because we're picking products, we're doing products, adding products and subtracting products of each row and each column. So if we multiply one row by 5, for instance, then that 5 is going to be preserved in all of the multiplications, which means that it's going to be preserved in all of the additions. And that's why that 5 shows up if we multiply 5 by one row. If we multiply 5 by a second row, then there's going to be two 5s that are going to be preserved on each product, and so forth. So from the definition, it is fairly straightforward that we have that linearity property. But there is a second part of linearity. Linearity means that we can multiply by constants and things are going to be preserved the same way. Row linearity. And also, if we add things together, then they're also going to be preserved. So row linearity also deals with row addition. Yes. Let's say, okay, so we know, let me come up with an example. Example 9 of what I mean here. 3, 4, 5, 6, 7, 8, 2, 1, 9. We know that the determinant of that is, I have to go back. Oh, I think I just realized there's a small mistake here. In example 8, we have 3, 4, 5, 6, 7, 8, 2, 1, 9. Yep. Oh, the determinant of this is negative 27, not 27. So this should be negative. And so this is negative, and that should be negative 3,375. Yep, sorry about that. That's example 8. I forgot to realize that this guy is negative 27, not positive 27. Let me double check example 7. Let me double check. Oh, here we swap. In example 5, we did swap 2 rows. So the 27 positive is good. And here the swapping was preserved in example 6 and 7. In example 8, I went back to the original matrix. Yep. So there was no swapping of rows, so there should be a negative 27. Okay. Whoa. Okay, so this guy is going to be negative 27. Okay, now that that is clear, let's move on. Okay. What if we add 1 to each one of those numbers? What if we have 4, 4, 5, 6, 8, 8, 2, 1, 10, 2, 1, 10. So, whoa, if we add 1 to each one of those, actually this was more complicated than what I anticipated, but that's okay. Okay. No, sorry about that. I'm gonna take this because it's overly complicated. Let's just add 1 to the first coordinate here, not 1 to the other two. Hang on. Okay, so let's say the 3 got changed into a 4, 7, and 9. Yeah. Whoa. Yeah, this is going to be longer than I anticipated, just with that little change, but that's okay. One way to address that is to say, okay, this is the same thing as the original one, 3, 4, 5, 6, 7, 8, 2, 1, 9, plus 1, 0, 0, but then just the row is the only one that gets broken up into two rows. 1, 0, 0 plus 3, 4, 5 is 4, 4, 5. And then we have 6, 7, 8, 2, 1, 9. So that's what linearity means, row linearity. If we can break up one row into two rows by addition or subtraction, as long as we keep the rest the same, we're good. Now, what is the advantage of doing that? This guy, we already know, is negative 27. So we don't have to redo this anymore. This one may be easier, and in fact, it is easier. Typically, when we have more zeros than not on a matrix, finding the determinant is way easier because there's going to be more zero products that we don't have to add or subtract, because adding or subtracting zero doesn't change anything anyway. So we know this is 27, rather negative 27. Now, we still have to figure this out. But this one is easier to figure because any product with zeros is going to be zero anyway. So we really have 1, 7, 9. I'm going to do that here. So 1 times 7 times 9. And then 1, 8, 1. 1, 8, 1. And that's going to be negative, isn't it? So we got 1, 2, 3, 1, 3, 2. So there's a swap to put it back into 1, 2, 3. Yeah, so that's going to be negative. The parity is odd, so we put a negative in it. And then I close the parenthesis because 0, 6, 9 multiplying together, 0 times 6 times 9 is 0. 0 times 8 times 2 is 0. 0 times 6 times 1 is 0. 0 times 7 times 2 is 0. So all of the other terms are going to be 0. That's why I'm not, there should be 6 terms altogether. 1, 2, and then 3, 4, 5, 6. But all of them are going to be, well, 4 of the 6 are going to be 0. So why write them down? So we got negative 27, 63 minus 8, 55 plus 55, 63 minus 8, yep, 55, and then 15 minus 7 is 8, 4 minus 2 is 2. So now we know that this matrix has determinant 28, or this determinant is 28. Yeah, yeah. But as usual, I'm going to check with calculator. So I'm going to edit and we're going to change that into a 4. 4, 5, 6. Oh, so 6, 7, 8. That goes back to 9. 1 and 2 going to the left. Exit. Find the determinant. Sure enough, 28. So we're good. It's always good to double check because there are too many little computations going on here, and we don't want to make too many mistakes. So we can add things or subtract things as long as we keep the rest of the matrix the same, though. That's an important consideration to keep in mind. Yeah. Yeah. So this is a nice way to add zeros to a matrix, yeah, to start breaking matrices down into smaller or simpler numbers. Okay, so we got row linearity, very, very important property. Another property, property number 4, if two rows are equal, if two rows are equal, then the determinant is 0. Right away, it is 0. So let's say we have, as an example, 10, some big numbers, some weird numbers, -7, 13, 8, 5, 92, 77, -7, 13, 8. As you look at this and observe it, oh, we got the same row in two places. The determinant is 0. No questions asked. Well, yeah, just property number 4, or very short answer. Why? Because of property number 4. And the reason is because, okay, we're going to have this product, for instance, but then that product is going to repeat this way, because -7, 92, 8, -7. When we pick this number, we're going to do the same product. Invariably, one is going to be positive while the other one is going to be negative. So the products are going to show up twice, the same products. So like 13, 5, 8 is going to come out of that 2, 1, 3. But then we're going to have the same product here, 8, 5, 13. And they're going to have opposite parities. So they're going to cancel each other out. And that's why. So if we have the same row twice, or 3 times, or 4 times, it doesn't matter, but at least twice, then the whole thing is going to collapse and become 0. Because we're going to repeat products. Some of them are going to be positive. The other ones are going to be negative. And that's it. Okay. Property number 5. When we were eliminating elements of matrices, we heavily use this operation. So the elimination row operation of taking one row and then adding a constant times a second row. Remember when we were eliminating? The elimination row operation does not change the determinant. Okay, let's look at an example. I know I'm using the same example several times, but there's comfort in using the same example several times. Okay, let's say we want to do 3, 4, 5, 6, 7, 8, 2, 1, 9. And we wanted to do this determinant from scratch. I know the answer is -27 because that was example 2. But let's say we wanted to do this from scratch. Well, we can eliminate, I see a 1 here, and that makes things, well, which one do we, I want to eliminate as many as possible. We can eliminate this 7 by subtracting 7 times this 1 from this row. So the determinant will be by doing, actually we're going to do 2 row operations. Row 1, take away 4 times row 3. So this row, 4 this row minus 4 times this row is going to give us 3 minus 8, negative 5. 4 minus 4, 0. 5 minus 36, negative 31. And then we're going to do row 2 minus 7 times row 3. Yeah, because then 6 minus 14, negative 8. 7 minus 7, 0. Whoa, 8 minus 63, negative 55. And then we have 2, 1, 9. Well, after doing those kinds of row operations, this matrix will have exactly the same determinant. The determinant is still going to be negative 27. Unless I made a mistake in the computations, again, this matrix will have the same. And then we can simplify. Well, the thing is, we got this pivot. I kind of started out the wrong way. Really, I should have started by getting rid of those, but I wanted to use a 1 right away. Anyway, if you do any kind of row operations like this ones, now mind, there's 3 kinds of row operations. Swapping rows, that changes from positive to negative and from negative to positive, the determinant. If we multiply one row by a constant, and that's it, then the determinant gets multiplied by the constant. If we add a multiple of one row to another row, that does not change the determinant. So this guy will have the same determinant. Now let's check. So if I multiply 5 times 0 times 9, that's going to be 0. 5 times negative 55 times 1, oh, that's not going to change. So we're going to multiply negative 5 times negative 55, and that is, what permutation of columns is that? Is 1, 3, 2. So 3, 2 gets, so that's going to be 1. 1 swap brings us back to 1, 2, 3. Okay. And then we got 0. All right, 0 times this times that is going to be 0. I'm not even going to worry about whether it's positive or negative. We don't really care. 0 times this times that is going to give us 0. It could be positive or negative, but again, either way, it's not going to affect the product. So that helps. And then we're going to have negative 31, negative 8, 1. Negative 31, negative 8, and 1. Oh, here in this product, I missed, what did we do? Negative 5, negative 55, and 1. There's a 1. I did not write that down because multiplying by 1 does not affect, but we should show that there's 3 things we're multiplying together. Now, should we put a plus or a minus on that product? So the permutation comes from 3, 2, no, 3, 1, 2. I'm going to copy the permutation. 3, 1, 2, 3, 1, 2. How many swaps do we need to put it back into 1, 2, 3? Changing those two goes to 1, 3, 2. Changing those two goes to 1, 2, 3. Even, so we put a plus. And then we have this times that, plus or minus 0. The reason why I put plus or minus is because I don't know whether we're going to put plus or minus, but it doesn't matter because we're going to, either way, we're going to end up with adding 0 or subtracting 0. Anyway, 55 times 5, well, 5 times 5 is 25, carry 2. 5 times 5 is 25, 27. How many negatives do we have? 1, 2, 3, negative. Here we got 2 negatives, so plus 8 times 1 is 8. 8 times 3 is 24. Okay, so 15 minus 8, 7, 21, no, 27. Oh, but we borrowed 1. So 26 minus 24 is 2, but we're doing negative. Sure enough, the answer is negative 27. But that was no coincidence. Every time we're doing a row operation of this kind, we will not change the determinant. So maybe we should make a table of row operations and what happens to the determinant. So row operations and what happens to determinant. Well, we're running out of ink. Okay. So new pen or okay, so what happens to the determinant? If we multiply one row by k, multiply one, and by one I mean any, but only one row by k, then the determinant gets multiplied by k. Multiply determinant by k. Okay, that's one row operation that we know of. If we swap rows, swap two rows, then multiply determinant by -1. That way, if we have positive, turns negative. If we start with negative, multiply by -1, we end up with positive. And if we do elimination by, Ri minus a constant Rj, then determinant does not change. Does not change. So a common thing that teachers do is that they give you this big gigantic matrix, like a 5 by 5, and you got to find the determinant. It turns out that if you eliminate, and eliminating happens fairly quickly, you can get a matrix with a lot of zeros in it. And once it has a lot of zeros, then finding its value is very, very straightforward. Very, very straightforward. So just be aware of that. Use properties of determinants. The determinant of, so property number 6, we are still on properties. Determinant of the zero matrix, so, with a bunch of zeros, is going to be the 0, which makes sense. We're multiplying zeros all together. This one is not so obvious, number 7, but it is handy, very, very handy. The determinant of the transpose of A is the same as the determinant of A. Whoops, I'm using a capital letter for D, but it doesn't make any difference. It's still the determinant. So the transpose, is the same as the original determinant. Interesting. Let's make an example out of that, or with that property in mind. Let's look at example 12. 3, 4, 5, 6, 7, 8, 2, 1, 9. Let's say we want to do this again. And I know we already did this a couple times. And then the determinant is going to be unchanged after doing row 1 minus 4 times row 3 and row 2 minus 7 times row 3. And we're going to end up with, as we did, -5, 0, -31, -8, 0, -55, 219. The reason why I'm doing that is because when we think about this, if we change the rows into columns in the same order, the determinant is not going to be changed. That's what we just established in the last property, property number 6. No, property number 7. So if we put -5, 0, -31 as a column, -8, 0, -55, 2, 1, 9, then we're good. The determinant does not change. This is the transpose of that matrix. And we could have done that at the beginning too. It doesn't matter where you do it. If you do it, nothing changes. But what that does is that it allows us to do more row operations to get rid of the 2 and the 9. So we can subtract from the first row twice the second row. So row 1 minus 2, row 2, and we're going to end up with, well, that is easy, -5, -8, 0. And the more zeros we have, the better. On top of that, we can subtract 9 times here. So row 3 minus 9 times row 2, and the determinant is going to be equal. So, and we're just subtracting once. We're subtracting this row rather. So 0. Yep. Again, the more zeros we have within reason, the better. Yeah, we still have to multiply this times that, this times that, but then all the other products are going to be 0. Yeah, so we're going to end up with -5 times 1, -5 times 1 times -55. So that is 1, 3, 2. And then -8, 1, -31. And that is 2, 3, 1. 2, 3, 1. We need to swap those two. No, we need to swap those two. 1, 3, 2, and then we swap. So that's even. So that's a plus. Yep. And that's going to give us the same numbers. I guess with this particular matrix, we didn't add too much value to the computations because those two zeros were already giving us a bunch of zeros. Those zeros did not help us much. If we were simplifying, perhaps, yeah, if we were getting rid of this -5 by simplifying, then that would probably do better. Add more zeros that were more significant. But at that point, we may end up with fractions, which may complicate things anyway. So it's the same product is going to happen. Here, we're going to end up with a -275 plus 248. And that's going to give us -27. Okay, a few more properties very quickly. Very, very important property. Property number 8. If A is singular, then determinant of A is 0. If A is invertible, then determinant of A is not 0. So there's a strong connection between whether the determinant of a matrix is 0 or not 0, and whether the matrix is not invariable or invariable. So not 0 means invariable, 0 means non-invariable. And property number 9, determinant of the product, this is an important property, is equal to the determinant of A times determinant of B. You can multiply the two determinants and end up with a determinant of the product. There's one more determinant rule or property that we need to establish. 10. If you have an upper triangular or lower triangular matrix, all you have to do to find the determinant is multiply the elements in the main diagonal. So if A is upper triangular, upper triangular, there should be a space in between those two, or lower triangular, then determinant of A is equal to the product of elements in main diagonal. Okay, so as an example 13, let's do a new example. 13, say you have 1, 7, 98, 107, 0, 2, 55, 2020, 0, 0, 3, negative 81, 0, 0, 0, 4, and we want to find this determinant. We have enough room in this page to do that. It's upper triangular, which means there's a tons of zeros here. This is the main diagonal. And it really doesn't matter what those numbers are. The answer is 1 times 2 times 3 times 4. 1 times 2 times 3 times 4, 24. If you put this into the calculator, you're going to get 24. Can guarantee you. Why? So we multiply one element from this row and this column. So this element is one of the products we have to do. But then if we change to another, so from this column, we move to this column, then on the next factor, we have to do this guy or 0. But if we pick this one, then the remaining factor is going to be 0. Either way, we're going to multiply by 0. So that's going to be 0. If we move on to this guy, so 1 times this guy, then we got to pick one of those two, and then after that, one of those two that is not on the same column as the previous column that we picked. So the bottom line is that we're not going to, the only way to avoid the zeros is by going this route. Any other product will contain zeros in it. You know, if we go with this guy, then you can pick one of those two next. Let's say this one. Okay, that's fine. Those two. And then we got to pick, see, on the next row, we cannot use the same column. So there's only zeros left over. If you go and do 107 and 2, then we can pick 0 or 3. If you stay with the 3, then the next number has to be 0. So there's no way to avoid zeros with an upper or lower triangular except in the main diagonal. So that is an easy way to obtain determinants. And there's one more thing we have to do, which is the finding determinants by minors. Finding determinants by minors or cofactors. Yeah. So I'm going to bring back our old example. I should have memorized it by now, but example 14. 3, 4, 5, 6, 7, 8, 2, 1, 9. Let's say you want to find this determinant. Attached to any matrix, we have what is called the matrix. I call it matrix of signs. Matrix of signs. Okay. So the 2 by 2 matrix by signs is going to start with the upper left corner being a plus and then alternating. So that is a 2 by 2. A 3 by 3 starts with the upper left corner with plus and then everything else alternates. So minus, plus, minus, plus, minus, plus, minus, plus. A 4 by 4, same thing. Start with that and then alternate everything else. Plus, minus, plus, minus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, and so forth. We're going to use this. This tells us, this is an easy way to tell whether, well, not really. It is an indirect way to figure out whether a parity is going to be even or odd. This is going to help us figure that out. But it doesn't give us the parity at once. Okay, choose any row or any column at random. Any row or column. Let's say we want to pick this. Now let's start with this column. So choose any row or column. And then start with the top one or the one on the left. It doesn't matter, but start with that. So the determinant is the number 4 with the corresponding sign from the matrix of signs, negative. So that negative comes from here because the 4 is in this position. So we pick negative 4. If had that been negative 4 to start with, then we still add another negative and make it positive. So whatever it is, we change the sign because there's a negative there. Form a matrix or a determinant in which this row of the 4 and the column of the 4 are gone. So we end up with 6, 8, 2, 9. 6, 8, 2, 9. Okay, 4 is done. Move down to the 7. 7, the position of the 7 has a plus on the matrix of signs. So do plus, I'm going to put the 4 in parentheses, plus 7 times the determinant found by crossing off the row of the 7 and the column of the 7. So we have 3, 5, 2, 9. 3, 5, 2, 9. Then move on, so the 7 is done. Move down to the 1. The 1 has a minus, the position of this element has a minus, so we do minus the number, whatever it is, times the matrix or determinant found by crossing off the row of the 1 and the column of the 1. So we have 3, 5, 3, 5, 6, 8. 3, 5, 6, 8. Okay. So now the problem of a 3 by 3 matrix gets reduced to a problem of smaller determinants. And then those are fairly quick to do. Whenever you have a 2 by 2 matrix, yeah, A, B, C, D, multiply the main diagonal, AD, and subtract the other diagonal, the product of the other diagonals, CB. So AD minus CB, that's it. So that's very quick. Let's do 6, 8, 2, 9. 6, 8, 2, 9. So multiply those two, 54. Subtract that, minus 16. 14 minus 6, 8. 4 minus 1, 3. 38. So that is negative 4 times 38. Plus 7 times, okay, 3, 5, 2, 9. 3, 5, 2, 9. 27 minus 10. 17. Now, I usually don't do that on a separate piece of paper. I just don't want to, what did I say? 17. I don't want to, well, I guess we can do that here. Minus 1 times 3 times 8 is 24, minus 30. Okay, so negative 32, carry 3, 15, plus 7 times 7 is 49, we carry 4, 111. That's negative 6 times negative 1 is positive 6. So we really have 125 minus 152. And then when we subtract 12 minus 5 is 7. 14 minus 12 is 2, but we are doing the negative, which is the biggest one. Yeah. So we end up with the same answer. This is another method. And this method works for any size of a matrix. So if you have a 4 by 4, take any, it doesn't have to be the middle one. You can pick any row or any column, and then we reduce the matrix into one size smaller. So if you start out with 4 by 4, then each one of those matrices, which would be 4 matrices, would be a 3 by 3. And then in turn, each one of those 3 matrices or 4 matrices, if we had a 4 by 4 to start with, would have to be broken down into 2 by 2s. Yeah. So either way, there's a lot of computations to be done. Yeah. Yeah. All right. With this, we're going to close this video about the determinant function, even though I didn't clarify what the function was exactly as a function, but it is a function, and 11 properties, including property number 0.